Hello YouTube, it's been a hot take, but I ran across two situations last week that are good candidates for a video. So today we're going to walk through a somewhat controversial topic in measurement, and that involves wanting to align scales that aren't themselves naturally aligned. Basically, you're trying to salvage data when the broader textbook recommendation is pretty universal in telling you that you need to collect new data. We're going to go off-roading from those textbooks and focus on two different forms of misalignment. The first represents a pretty common request that psychometricians get from either students or clients, and that is to just combine responses from items or scales that have different ranges of values. The most common situation here is to encounter items that have different numbers of response options, and somebody wants to get them together. That's always been frowned upon, but we'll talk about how to do it in a way that's most defensible from a measurement perspective. The second scenario has historically been framed as an issue of range restriction, but I'm going to use the term value compression here. Hopefully you'll get a sense of why I'm using that different term once we get to the application stage of this video. This is a situation that's new to me, but will likely be growing as machine learning, AI, and other big data advancements continue to be incorporated within psychometric applications. So there's a number of different ways of dealing with these situations, but I'm just going to go over two here today. The first method is a little bit hidden by our tradition of starting numerical sequences from a value of 1 instead of 0. But if we violate that tradition, we can construct and apply ratio conversions. And these are pretty useful for aligning scores from items that have different numbers of response options. The second method we'll go over has a very strong history of application within a different testing context, but we maybe can apply it here as well in limited applications. It may be particularly helpful for our value compression scenario. Lastly, we're walking on kind of methodological thin ice here, but these are scenarios that every psychometrician will encounter at some point or another, so I want to offer some solutions other than, sorry, we're not supposed to do that. So I'll try to address some of the cautions and concerns about pursuing this taboo practice before we get into the actual data exercises. In those exercises, we'll take a look at the two scenarios I just encountered last week that prompted the creation of this video. The first very common circumstance where you will be asked to do some tinkering is when someone has data that represents items with different numbers of response options. Take a look at the example here on the left. These four how hot is it items range in possible response values from 7 to undefined to 11 to 5. These response scales all have different semantic labels as well, which we won't really be getting into today other than making a brief note of caution at the end. The issue here is someone wants you to create a scale composite across these item responses. The textbook answer is you don't do that, but we'll present two options if someone twists your arm. The second circumstance is kind of a new one to me, and I'm calling it compression. There's a very well-established literature on restriction of range and how that can affect things like summary statistics. For example, the graph on the right here is trying to demonstrate the effect of range restriction on the sample correlation. The entire range of X values extends from 10 to 50, while the Y values go from 50 to 110. For various reasons, it's not at all uncommon in the social sciences to have data that's truncated, usually at high or low X or Y values. What we want is the full scatter plot here that's described by a correlation of 0.82. If, however, we only receive data with X values ranging from 10 to 20, our correlation of values within that compressed range would be 0.51. If we only received responses from people who had X values between 25 and 30, our correlation would be 0.18. The scenario we're going to go over is analogous to this, but kind of subtly different. So what we're dealing with here is really a matter of kurtosis if we're just looking at frequency distributions. The upper distribution has a compressed range of X variable scores relative to the lower distribution. The scenario that was new to me was one in which a predictive statistical model was spitting out values in a leptokurtic distribution, and if values actually matter, which they sometimes do, that might be a problem. So this second scenario is one in which we're going to rescale from a compressed range to an extended range of values. We got to be really careful on this one because sometimes values are meaningful and sometimes it's the distribution that you're more interested in. If it's the placement of the distribution that you're more interested in, then what we're going to cover might be helpful for you, but you got to be really, really careful because typically it's the values that are more meaningful. All right, so let's cover the first approach where we just apply pretty simple math. There are some features of this approach that make it particularly appealing for situations where you have items with different response scales. Probably the most appealing feature is that your scale endpoints will be exactly matched. Secondly, you can do this either at the item level or the aggregated scale level, which can really come in handy. And then finally, you can either go from larger to smaller or smaller to larger with this method. By that I mean, if you have a 5-point and a 7-point scale that you're trying to align, you can either go from 5 to 7 or 7 to 5. The only real trick to this alignment strategy is that you need to start your assignment of numbers at 0. This isn't really typical with psychological assessment data, so make sure to confirm how your data has been coded before you do this transformation. What I mean by starting at 0 is that for our first example item here, the options would be represented by a 0, 1, 2, 3, 4, 5, and 6, and not the number 1 through the number 7. Once we determine our numbering sequence for both scales, we apply the ratio equivalence formula we all learned in 6th grade or so, and place the value of your old scale over the highest possible old scale value on the left, and the unknown but desired new score value over the desired new score maximum on the right. Applying the math of 1 times 4 divided by 6 gives you the desired scale value for your old scale response, here 0.67. If we wanted to instead express the 5-point scale response on the 7-point scale metric, we just swap out the left and right values. So here, some would agree is coded at 3, and that goes in the numerator in our left-hand ratio. The highest possible value for the bottom item is 4, so we put that in the left-hand denominator. We don't know what the equivalence is when expressed on the 7-point scale, so we just use the ubiquitous x to represent that. We divide by the highest possible desired scale value. Again, applying the math, we get our estimate of 4.5. So just applying the elementary school ratio equivalence formula can be applied when you have items with different numbers of response options. Well, don't do this without some careful thought. Because again, this isn't a best practice recommendation. This is more of a, oh shoot, how am I going to get out of this mess recommendation. Okay, so our good old reliable z-scores are going to be our second option for tinkering. Unlike the ratio equivalence, we're going to lose our clean landing on desired endpoints. Also, you're probably only going to find this useful with aggregate scale scores instead of individual item responses. Although I'm presenting this as an approach to apply with data compression, it's really just a generic approach to changing the location and spread of a distribution of scores relative to some fixed set of values. Again, sorry for the busy graph. I got to find some disincentive for these, but let me walk you through slowly here. First, take a look at the upper right hand and lower right hand distributions. They both look somewhat constricted to what we generally expect to see. Green bars look like they suffer from some sort of floor effect, and the yellow bars just look a little smudged. It's super important here to note that usually these locations and spreads are meaningful, and you're not going to want to do any sort of transformations whatsoever. However, in the context of what I've been doing in my work, I do sometimes need to rescale these distributions. What we're trying to do with both of these is to move the distributions such that the range of scores align with values that we expect to see or need to have. So we're going to use an old z-score transformation that's very common in testing applications, and that is to construct a standard scale score, here represented by the SS left-hand element in the step 2 formula. First, we'd simply rescale our values as z-scores, and then we apply the desired midpoint and standard deviation, represented here by mu and sigma. Now, for mu, you'll likely want to reference the old scale mean. For example, if I'm trying to move from a scale of 1 to 5 to a scale of 1 to 7, the scale midpoints are 3 and 4, but those aren't likely to be my actual empirical averages. So you'll most likely want to apply the previous ratio equality formula to your old scale average and use that as your desired mu. Your sigma you're going to have to play around with a little bit to get your desired range. You won't land exactly on your desired low and high values, but you can get close. All right, so there's more than a few cautions with these approaches that you should be aware of, and this isn't an exhaustive list. These are just some pretty much off the top of my head thoughts. The first caveat is that it's probably inappropriate to try to combine responses that not only have different numbers of response options, but also different semantic labels. Yep, I agree, that's not ideal, but again, sometimes we're stuck and we need to get out of a mess. The second cautionary consideration is that, especially with the ratio equivalence approach, there's an implicit assumption of equal intervals between scale points. Now, this is kind of related to the semantic label issue, but almost certainly violated here. Thirdly, you're going to have the appearance of playing with variance because of shifting scales, if for nothing else, just for the numbers that are being used. You can also alter variance by introducing or restricting the number of response options under consideration. This is never good, and probably the number one taboo for psychologists, statisticians, psychometricians. So if you do pursue some of these transformations, make sure you really dig into your data and understand what it looks like before and after. And make sure to document all of the transformations you did and how those may have affected your results. Lastly, make sure you're especially careful with those Z transformations. I included and deleted those slides a few times because I know this strategy will be used by someone in a way that really messes things up for them. Generally speaking, the location and spread of distributions are super meaningful, so you're only going to want to tinker with those in very, very limited applications. All right, did that scare you enough? Technically, I'm not a professor anymore, so I can participate less reluctantly in contributing to your delinquents. I do still feel pangs of ethics every now and then. Ah well, let's be deviant here and play with some data.
So I've gone ahead and already populated the environment here with some of the objects that we need to demonstrate the scenario that prompted this video. And the scenario can be seen here in this figure. And so what's going on here is on the x-axis we have a range of values. They're not all listed here, but a range of values roughly from 1 to 7. And on the y-axis we have 1 to 5. These scatter points are jittered, so they don't print over each other, but these exist in linear arrays over the x-axis points. But what we have going on here is there's a bunch of green dots and only green dots in the high plotting space here on the x-axis. So between points of roughly 5 and 7, I only have green dots. That's telling us that something odd is going on. What the color coding here is reflecting is this particular data set is looking at the relationship between support from different sources and your general well-being at work. And so the sources that we have here are coworkers, supervisors, and family. And so the coding is such that the green is reflecting supervisor support. So something's up with sup here, and we need to take a look at that. So before we actually do our alignment exercise, let's go ahead and confirm that in fact these 3 different forms of support may be expressed on different ranges of scales. So I'm going to actually use the describe package frequency function because that gives me a frequency table as well as I can't type and think at the same time. Frequency table as well as a visual. We'll look at coworker support, the pink one first. 1 to 5. There's a little straggler, probably NA over there, and yep, it looks like those are NAs. But those are 1 to 5 values that we expect to see on typical Likert type or semantic differential scales with a 1 to 5 rating, as long as this is an aggregate, and in fact this is an aggregate, not individual items. So let's look at, what was our other one here, FAMSUP. 1 to 5, with again maybe 1 or 2 NAs there placed at the end. Looks like a fairly well distributed set of scores there. And then the one that we're suspicious of, and it looks even more suspicious when the plot isn't blown up, when it's compacted a bit. You can really see that grouping of greens there. So sup, I didn't come up with these variable names. I certainly didn't come up with a variable capitalization scheme because I hate that mixture. It doesn't seem to want to zoom for me, but we'll try to expand it here and take a look. Definitely different from the 1 to 5. It's more of a definitely negatively skewed distribution. There's a ton of 7s. That we're suspicious of that as well in terms of maybe some leniency or elevation of ratings, but we're not going to deal with that today. Oh my goodness, 231, 332.5, a third of the responses here on the scale. It is a scale, not individual item responses, but fully 1/3 gave full elevated rating here across the items. I don't recall how many items are on the scale, but we can investigate that later. That's not the point of this current exercise. The strategy is let's express all 3 of these forms of support on the same scale so we can provide them in the same visual. So we'll actually go ahead and apply our ratio equality formula, and we're going from a 7-point to a 5-point scale. Since 2 of them are already expressed on 5-point, it makes more sense to do less work. We'll take the 1 and move it to 5 instead of taking 2 and moving them to 7. However, we have to remember our caveat, and our caveat is that we need the starting point on these scales to be 0. So it's currently 1 to 7, which is typical, not universal, but it's the way that work psychologists, industrial psychologists tend to code their data. And so first, let's actually go into our data and re-express this on a scale of 0 to 6. Now, normally I wouldn't do this, but because this is just for demonstrative purposes, I'm going to overwrite the previous variable. And I'm going to do that because I actually have code here to transform the raw data into long format such that we can plot it easier. And so that's why I'm going to just overwrite the old variable. So we'll just subtract 1 from each value, and that should do it. If we go ahead and take a look at the new frequency distribution, we see that it's on now a scale of 1 to 6, which is what we expected. So now we can do our transformation. And again, not something we normally do, but I'm going to overwrite it. And actually, even though this isn't best practice, it's not the end of the world as long as we script and save our script and generate our script from top to bottom in terms of what we do earlier, what we do later, so we can reproduce it and correct the mistakes once we make them, because we will make them. So I'm actually going to take support, sup, and I'm going to multiply the highest value on the scale I want to express it on. Now, again, that scale looks like a 1 to 5, but we have to rescale it to 0 to 4. So the 1 to 5 scale on a 5-point scale starting with the number 0 is going to have a maximum of 4. And then we're going to divide by the maximum on the old scale, which is 6. We go ahead and rescale sup, and then take a look at it. And it's on that 0 to 4 scale, which is what we want. It's not the ultimate thing we want. What we want is the 1 to 5. So we'll go ahead and bastardize this variable a little bit more, and we'll add 1 to it. See if I can spell it right this time. And we'll take a look at that distribution. And there it is on our 1 to 5 scale, which is what we were hoping for. Now, if I put that into long form and then ask for the plot again, we should see that the plot now has our 1 to 5 scale. And again, we just want to make sure to document what we did, that this sup was originally specified on a 7-point scale, but we recalibrated it such that visually we can present this information together. Okay, so I'm going to take a second to load up the second data set, and I'll be right back.
A few moments later.
Okay, so I've loaded up the data that should be demonstrative with regard to what we were talking about in the slides. The object, the frame that contains the variables that need to be expanded, whose distributions are what I'm referring to as being compressed relative to the scores that we need to see exhibited, is predictions 2. You can see that just to the left of my big fat head there. And we'll do the same thing. Take a look I cannot spell this morning. And we'll see what that looks like. We'll take a look at the base histogram and see if that gives us a better picture here. There we go. So let me try to zoom this, and we see compressed. Again, my big fat head in the way. What we need on this scale is we need values ranging from 1 to 4, and what we have is predicted values ranging from 2.4 to 3.2. So we're going to take the opportunity to rename these variables in this particular case. We can keep the predictions too, and we'll just call it z-score. And we're going to use the base function scale and it's always a good idea to take a look and make sure that your Z transformation worked as you wanted it to. So let's just do a mean and standard deviation. Oh my goodness. And that looks like it's a big number. It's actually a really small number. That e to the negative 16 is a scientific notation, so that's saying it's essentially 0 and 1. If you don't believe that, if you don't trust it, you can use the psych package. That describe function is really, really handy. We'll just do the whole object. I'm going to expand this so the table comes in formatted nicely. And there's our table. It didn't come in as nicely as I hoped it would, but we see our z-score, mean, and standard deviation here. When it's rounded to the 100th spot, you don't get the silliness with the scientific notation. So you see that the mean and standard deviation are in fact 0 and 1, which is what we want to start with. And now we're actually going to, you know what? We can also use the mean of the variable that we're transforming to use as the basis of our fulcrum. So in the slides I mentioned that when you're using this standard scale transformation method, you may want to base the mu off of the old mean on the raw scale. And so the raw scale here has a mean of 2.77. So we're going to use that. We're actually going to make our standard scale score. We'll put it in that object again. And using our z times sigma plus mu formula, we'll take the predictions z-score, multiply it by, now here we're going to have to, this is the aspect that you're going to have to play with a bit. So with a normal or approximately normal distribution, which this looks approximately normal, so scores are bunched in the middle. With an approximately normal distribution, your expectation is about 2/3 of the scores are going to be within 1 standard deviation above and below the mean. About 95% of your values are going to be within 2 standard deviations above and below the mean. And so that 2 standard deviations benchmark is a fairly decent one to try to help you figure out a starting point for how you want to play with your sigma. And what I mean by that is if I'm aiming for 1 and 4 as my endpoints, I have this fulcrum or pivot point of 2.7. We should write that down right before we forget it. By we, I mean me. So let's go ahead and do our order of operations here again. And what I'm blathering about is if we use that 2 standard deviations as kind of an estimate for where we expect the majority of scores to fall, and we have 2.77 as a fulcrum, the difference between 2.77 and 4 is about 1.3. The difference between 2.77 and 1 is about 1.7. So 1.3 and 1.7, that's about a 1.5, right? Now that's 2 standard deviations. I almost gave you all the finger, I'm sorry about that. So that's 2 standard deviations, so we have to cut that in half. So if we start with a sigma of 0.75, that two of those sigmas should get me to about 4 and about 1. Now, we have outliers here, so it's not going to be universally true. Again, this method doesn't stick the landing, but it's decent for a starting point. So let's actually try that and then take a look at that frequency distribution as well. And see if we can expand this a little bit. I'm having real issues with my Zoom this morning. Sorry about that. That looks pretty good, actually. So again, I have some beyond 1, I have some beyond 4. That's going to happen with this method. That's okay, because for my purposes, I can round those, and those become effectively 1 and effectively 4. The point that I'm happy about is I get some values in my 1s, I get some values in my 4s. If I wanted more values, I could just expand this standard deviation, and it's a good idea to play with this and see what actually happens. So if you really blew that up to a value of 2, and then took a look at that distribution, you see it's still going to be centered on the same value of 2.77, but now I've really blown those values up, and they're really stretching out beyond my desired values of 1 and 4. If we constricted it, it's going to give us values that are much closer, much more bunched, even more compressed around that mean value. So if we made a, for example, as long as it's there, we'll just make it a 0.2. Take a look at that frequency distribution. You see they're even more bunched than they were originally. So that 0.75 isn't too bad. I might want to go a little bit bigger to get a few more values out. But again, you're going to play with this. So this is something you're going to play with. And it's something that is probably only going to be applicable in very limited purposes when we talk about rescaling.
All right, that's about double the length I was shooting for, and I even cut up quite a bit. I'm gonna try to keep these at 10 to 12 minutes, but I'm still kind of learning on the fly here, so there's gonna be a few more speed bumps, I'm sure. Remember, regarding this current tutorial, these are not best practices. They're not techniques you want to apply regularly, but these are tools that can help you get out of a sticky wicket if you find yourself in one. Not going to belabor this one anymore, so thanks for sticking through it, and as always, please drop me a note if you have a question, comment, or suggestion for a future topic. In the meantime, happy psychometricing.